Today we're going to talk about constructing antiderivatives analytically. Your first project is due, so just put it in your folder before you leave. Next class, take-home quiz 1 is due. I just handed it out. I just want to read you the directions, make sure that everybody sees them. You may use a scientific calculator. If all you have is a graphing calculator, you can use it, but just don't use the graphing capabilities. Okay. You can use your textbook. You can use your class notes / the packets, right? But you may not use any other resources like the internet, the graphing capabilities of your calculator, or other people. There's no time limit. There's a recommended time limit at the top. That's just to sort of give you an idea of how quickly you need to be able to work when the test comes. Okay? But for this, you can actually use as much time as you want. Show all your work, no credit. Put a box around your final answers. And that's it. Okay, so this is due next class. Questions? Okay, so that's due next class, and next class I will also hand out project 2. Okay, so today we're going to look at rules for finding antiderivatives for certain elementary functions. These rules will be ones that we use repeatedly over the next couple of months. So as we figure them out, make a point to memorize them. All right, so we know that this integral represents an area. That says the integral from 1 to 3 of 8x cubed dx. What does it represent? Let's draw a quick picture. Okay, so the 8x cubed looks something like that, right? And what area am I looking at with respect to that curve? Between the curve and the x-axis, between x equals 1 and x equals 3. So I put on a 1, put on a 3, and I'm looking for the area between the curve and the x-axis from 1 to 3. So that's what those symbols mean. The area between the curve and the x-axis from 1 to 3. We can approximate the value of that area using a graphing calculator, but we could also do it by hand using the fundamental theorem of calculus. Okay, the fundamental theorem of calculus states that the integral from a to b of a derivative, f prime of x dx, can be evaluated by looking at the total change of the function, f of b minus f of a. So in this example, the fundamental theorem of calculus becomes the integral from 1 to 3 of 8x cubed dx equals f of 3 minus f of 1, because my a and my b are 1 and 3 here. Where f is a function such that f prime of x is 8x cubed. Can you find a function whose derivative is 8x cubed? Yeah. Go ahead, what is it? 2x to the 4th. Good, let's double check that. If I wanted to take the derivative of that, I would bring the 4 down and multiply by the 2. That would give me the 8. And then you reduce the exponent by 1 and you get the 3. So 2x to the 4th is an antiderivative of 8x cubed. It's a function whose derivative is 8x cubed. So to put it all together, fundamental theorem of calculus says that the integral from 1 to 3 of 8x cubed dx is equal to the antiderivative 2x to the 4th. And this is some new notation, so take note here. Evaluated from x equals 1 to x equals 3. Okay. So that means plug in the 3, plug in the 1, and subtract the 2. Okay. So when I plug in the 3, I just replace the x with the 3, and I get 2 times 3 to the 4th, minus what you get when you plug in the 1, 2 times 1 to the 4th. 162 minus 2 is 160. So that is the area under the curve that we're looking for. Evaluated? Yeah. All right, are there any other antiderivatives for 8x cubed besides 2x to the fourth? Sure, give me one. 2x to the fourth plus 1. Yeah, you can always add a constant because when you take the derivative of the constant piece, it becomes 0. All right, so let's see if that matters when we're using the fundamental theorem of calculus, if you use a different antiderivative. So we'll look at the integral from 1 to 3 of 8x cubed dx. Okay. That should be the antiderivative, which I used 2x to the fourth before as my antiderivative. Now I'm going to use 2x to the fourth plus 1, evaluated from 1 to 3. You can write x equals 1, x equals 3, or just 1 and 3. We'll do it both ways. All right, so what that means is plug in the 3, plug in the 1, and subtract the 2. So I plug in the upper bound, and I get 2 times 3 to the fourth plus 1 minus, and I plug in the 1, 2 times 1 to the fourth plus 1. Okay. So this is going to be 162 plus 1 is 163. And this is going to be 2 plus 1 is 3. And I get 160, which is the same thing I got before using the antiderivative 2x to the fourth. So it turns out you can use any antiderivative with the fundamental theorem of calculus. It will always give you the right answer, no matter what you choose as your plus c. So most people choose their plus c to be 0, right? Just choose the simplest thing possible. Okay. But it doesn't matter. You can use any c you want with the fundamental theorem. All right, so since finding antiderivatives is tied to evaluating definite integrals, we use integral notation to denote an antiderivative. So when I write this integral symbol without bounds on it, there's no lower bound and upper bound, no limits of integration, that means just find an antiderivative. So this says the integral of 8x cubed dx equals 2x to the fourth plus c. The process of finding an antiderivative is called integrating. So I want to integrate, get the integral of 2x plus 3 dx. That just means find an antiderivative. There are no bounds on the integral symbol, so you're just looking for an antiderivative. Okay, so I want an antiderivative of 2x, a function whose derivative is 2x. X squared. A function whose derivative is 3. 3x. And then you can always add a constant of integration. All right, so here's the vocabulary associated with integral notation. The entire left-hand side of the equation is called an integral. We've got an integral sign. Then the function itself is called the integrand. And dx tells you what the integration variable is. Okay. In Calc 2, when we're only dealing with single variable calculus, like that's the title of your book, right? The dx is going to seem unimportant, right? But once you move to Calc 3, when you're going to have more variables, this symbol is going to be really important because it's going to tell you what variable you're working with. Yes. Mm-hmm. Mm-hmm. Yep. All right, and then once you take the antiderivative of your function, x squared plus 3x, that's the antiderivative, and then the plus c is often called the constant of integration. So we would read that equation, the integral of 2x plus 3 dx is x squared plus 3x plus c. Okay, so when the integral sign doesn't have any limits of integration on it, there's no a and b, the integral is called an indefinite integral. as opposed to the definite integrals that we've been trying to find earlier, which means find the area under the curve. So the dx is a necessary piece of every integral. It always goes to the far right. For indefinite integrals, the plus c is mandatory. Omitting the plus c will cost you points. Okay. Finding antiderivatives is going to be really important for us this semester. We're going to do it a lot. Okay. So how do we find antiderivatives? So far we've been reversing our differentiation formulas. So that's what we're going to do. We're going to look at some of our basic formulas, try to figure out what their antiderivatives are. All right, if I want an antiderivative of x to the n, a function whose derivative is x to the n. It's got to be n plus 1 is my exponent, right? Right? Because then when I'm going to bring that n plus 1 down and reduce the exponent by 1, so I'll get the n in my exponent. But when I bring that n plus 1 down, I don't like it there because what do I want there? I just want a 1, right? So how could I make the n plus 1 cancel? Divide by n plus 1. Yeah. Does that make sense? So quick example, the integral of x cubed dx would have to be x to the 4th over 4. Right? So that when I take the derivative of x to the 4th over 4, I bring the 4 down, it's going to cancel with the 4 on the bottom, and I get just the x cubed. Okay. All right, antiderivative of e to the x. E to the x, yeah. Because the derivative of e to the x, I should have a plus c here, or I'll lose points. Okay. A function whose derivative is cosine x. Sine. I'm going to come back to this sum one. We'll jump to the other side here. A function whose derivative is 1 over x. Natural log. A function whose derivative is a to the x. Close. ln of a, yeah. All right, so the derivative of a to the x, is a to the x times the ln of a. So if I want to undo an a to the x, I know that a to the x, that has as its derivative a to the x is part of it, but the derivative of a to the x is a to the x times ln a. So to undo that times ln a, I should divide by ln a. Rewrite that. Yes. Yes. Yeah. We're just going to ignore that little detail for now. Yeah. Okay, how about a function whose derivative is sine of x? Negative cosine. Okay, and then these last two at the bottom are more general rules. If you want to take the integral of a sum of two functions, you can take the integral of each function separately. So this is going to be the integral of f of x dx plus or minus the integral of g of x dx. So sum or a difference, you can just do the two terms separately. And then if you have a constant times a function, you can just move the constant outside and integrate the function itself. So this is c times the integral of f of x dx. All right, so let's try to use our new formulas on an example. I want to take the integral of this function. There's three terms here. First thing I'm going to do is simplify some things using the last two rules here. If I want to take the integral of a sum or a difference, I can take each term separately. And if I have a constant coefficient, I can pull it outside of the integral. So I'm just going to rewrite this as 2/5 times the integral of e to the x dx minus 3/4 times the integral of x to the e dx plus the integral x minus 1 over root x. Let's do a little aside here. X minus 1 divided by the square root is the same thing as multiplying by x to the negative 1/2. And then distribute. So I would get x to the 1/2 minus x to the negative 1/2. So I'm just simplifying that because it's going to make taking the antiderivative a lot easier. So this is going to be x to the 1/2 dx minus the integral of x to the negative 1/2 dx. All right, so now I have 4 antiderivatives to take. All right, so I've got 2/5 antiderivative of e to the x minus 3/4 times the antiderivative of x to the e. Great, yeah, trying to trick you here. This is a power rule because e is just a constant. So this is x to the e plus 1 over e plus 1. Plus antiderivative of x to the 1/2. So you have to add 1 to the exponent. What would you get? 3/2. So we have x to the 3/2 divided by 3/2. To me, this is a personal preference. You could leave it like this if you want. But to me, dividing by a fraction, like creating a compound fraction, is kind of ugly. So what could I do instead of dividing by 3/2? I could multiply by 2/3. I'm going to do that. So this becomes 2/3 x to the 3/2. Minus, okay. Then we do power rule again on x to the negative 1/2. Add 1 to the exponent, and you get x to the 1/2. Yep, x to the 1/2, and then you would divide by 1/2 or multiply by 2. Plus c. All right, it takes some getting used to doing the derivative rules backwards, but with practice, you'll be able to go in either direction and feel comfortable with it. And you can always check your work by taking the derivative of your answer and making sure you end up where you started. Okay. All right. Note that there are lots and lots of integrals that we can't do yet. X times sine x, x e to the negative x squared, e to the negative x squared. Lots and lots of integrals that we can't do yet. Which is why we spend 1/3 of the semester learning how to evaluate integrals. All right, so for now, though, you're going to do some practice with the basic rules that we've learned so far. You're going to be finding both definite and indefinite integrals. Okay. So some of them will have bounds of integration, which means find the area under the curve using the fundamental theorem. And then others later will have no bounds, which means just find an antiderivative. All right, go ahead.